All right. Feels like it's been a while since I've made a video, so this is kind of interesting. We are getting back into some new content here, finally. And we are getting into some of the good stuff now, finally. We have spent quite a bit of time learning some fundamental chemistry knowledge. Atomic structure, our last unit, we learned all about protons, neutrons, and electrons. A lot about electrons, right? Electron configuration and Bohr models. And so what we're going to start doing today is getting into some of the good stuff, okay? Um, Everything that we've learned prior to today is important for you to know. Chemistry builds on itself, and so you're going to be noticing a lot of the things that we've talked about in the past are going to be coming up over and over again, starting with today. All right, so we're going to be talking about chemical bonding. I'm really just making this kind of like an introductory video. I don't want it to be too long, at least not yet. So hopefully I can keep this one relatively short, but I just want to give you guys an introduction into what chemical bonding is. Okay, and we're going to get way more in depth into it as time goes on. All right, so here are some of the questions that we're going to be asking ourselves over the next few weeks. So naturally, chemistry starts with like the smallest bits of matter, right? We kind of build our way up. So we start with atoms, and so that was the entire last unit, right? Learning about atomic structure. From here, we're going to get into bigger and bigger things, okay? So we're going to be looking at questions like this. How and why do atoms bond together, okay, to make bigger structures? Okay, how do atoms come together to make bigger structures? Can we predict what atoms are going to do when they interact with each other? Okay, the answer is yes. Okay, and we're going to learn about that. What kinds of structures do atoms make? Okay, you've probably heard the terms compounds and molecules before, so we're going to learn how these structures are classified and how to name them, and then how do these bigger structures interact with each other? Okay, and so we're going to be learning about intermolecular forces. This right here is going to take us the better part of a month. Okay, and so I'm going to be breaking it down into topic by topic, as best I can to help you guys manage it. But this is sort of the big picture of what we're going to be looking at over the next several weeks. All right, I want to show you this image. This should look familiar to you. I showed this to you guys in the follow-up video after we did the electron configuration periodic table activity. So what we've got here are the Bohr models of the first 4 rows of elements, with the transition metals not included. Okay, so remember the transition metals are the D block elements. Those are the metal elements that are sort of in the middle part of the periodic table. We're not going to be focusing too much on those guys, at least not in this class. They get kind of complicated and they like to break all the rules. So we're going to be focusing on these elements, which are referred to as the main group elements. This is column 1, column 2. Skip the big middle section, right? And then this is technically column 13, 14, 15, 16, 17, and 18. Okay, so this is on the far right-hand side. So once again, it's like the S block and the P block. These are the elements that we're going to be working with. These numbers up here, 1 through 8, instead of being the column numbers, which they aren't really, these numbers up here tell us how many valence electrons there are in an atom in that column. Okay, so you'll notice here in this first column, all of these elements here have 1 electron in the outermost energy level. Those are the valence electrons, or electron in this case, right? And beryllium, magnesium, calcium, these all have 2 valence electrons. Boron, aluminum, gallium each have 3, and the pattern continues all the way over here to the 8th or the 18th column, with the exception being helium, right? So neon, argon, and krypton all have 8 valence electrons. Helium is placed over here because it is a noble gas and it behaves like these elements, even though it only has 2 valence electrons. Okay, and that's due to the 1s orbital only holding 2 electrons, right? So, yes, so what is so special about those electrons? Well, let me put it this way, okay? In order to understand how atoms interact with each other, we have to know what the outside of the atoms look like, okay? Think about it like this, right? When 2 objects collide with one another, say 2 atoms, it's the outside of those objects that come into contact first, right? It's the outside that interact with each other first. So the electrons on the outside of atoms are really important. Okay, and once again, those are called valence electrons. Those are the electron or electrons in the outermost energy level. Okay, the ones that are colored red on this diagram here, or this graph. Not really a graph. Okay, and like I mentioned, the number of valence electrons in any given element is equal to its group number, assuming that you're skipping the transition metals, right? So 1, 2, skip a few, 3, 4, 5, 6, 7, 8, right? So if you take away the D block, there's only 8 columns on the periodic table, and there you go. Those are your valence electron numbers, okay? And so just to make sure I'm being very clear here, I can't really draw on this while I'm recording the video, but this is where my number 1 would be, number 2, number 3, 4, 5, 6, 7, and 8. Okay, this is the big section here in the middle that I'm skipping. And then definitely not going to be worrying about these guys down here. Okay, so the D and the F blocks we're not going to be worrying about too much for really the entirety of this unit. Okay, so if you have your hard copy of the periodic table at home, it might be a good idea to go ahead and just label this on your periodic table right now. The number 1, 2, 3, 4, 5, 6, 7, 8. And you can like point an arrow to each side saying that, hey, those are the numbers of valence electrons for the elements in that column. Okay, so for example, carbon would have 4 valence electrons. Bromine would have 7. Okay? All right, so let's get into our... one last slide here before we get into some examples. So the first big question that we're going to be asking ourselves is, why do atoms form bonds between one another? Like, what is a bond? What is it? Well, turns out this is actually a really, really difficult question for us to answer, and I don't want to bog us down into the details of that yet. We are going to get into that, obviously, but today is really just supposed to be an introduction, okay? So we're going to table these questions for now, come back to them later, once we know a little bit more about how chemical bonding works, okay? All right, so let's look at an example, okay? And this is my... well, I won't say it's my favorite, but it's one of my favorite chemicals. This is sodium chloride, okay? And we're going to look at, this is a compound, right? So I think you guys would be able to recognize that. Sodium chloride, it's made of sodium and chlorine, okay? And we're going to look at how, let me tell you a little bit of a story, right? Sodium, in its pure state, okay, so pure elemental sodium is actually like a soft metal. Okay, you can cut it with a butter knife, all right? It's explosive when it comes into contact with water, okay? So pure sodium has to be stored in oil so that water can't get to it, otherwise it will literally explode. Chlorine, pure chlorine, is a gas, and it's often like dissolved into pools and used as like a antibacterial or antimicrobial. It'll kill off little critters that are in your pool. If you open your eyes under the water too long in a chlorinated pool, your eyes will start to get red, and that's from the chlorine sort of attacking and messing with your eyes. You'll get a little bit of inflammation in your eyes due to the chlorine. So separately, sodium and chlorine are both kind of well, first of all, they're radically different, right? One's a solid, one's a gas. One's explosive with water, one is mixed into water. But also, they're both kind of like dangerous, right? Like sodium is, explosive when it comes into contact with water. Our bodies are like 75 to 80% water, right? So this is obviously not good for us. Chlorine is in pure amounts like toxic, right? And can make you sick if you are exposed to too much of it, and it'll hurt your eyes in the pool. But somehow, when sodium and chlorine combine or bond together, this becomes table salt, which tastes delicious, and we sprinkle it on our French fries, okay? So that's kind of what we're looking at today, is what on earth is this? Okay, and how does something like this form out of the two pure substances? Okay, so that's what we're going to be looking at today, and I'm going to be transitioning us over to my document camera here. All right, so we've got the name of this chemical here is sodium chloride. It is made from sodium and chlorine. Okay, and the first thing that I'm going to do is teach you guys how to draw something called a dot structure. Okay, these are very simple, very easy to make. Okay, a dot structure is just an element symbol that has dots around it, where the dots are the number of valence electrons that that element has. Okay, so if I take my periodic table here, here is sodium. Sodium is in the first column. It's going to have 1 valence electron, so I'm going to draw 1 dot there next to sodium. And here's chlorine. Okay, chlorine is over here on the right side of the table. It's in column 7, right, if we exclude the transition metals. So chlorine is going to have 7 valence electrons. It doesn't really matter how you draw these dots on here. Typically what people do is they pair them up, okay, like pairs of 2 on each side. And then, they try to spread them out as best they can while keeping them paired up if they have to. Okay, so there we go. All right, now we're not going to get into all of the nitty-gritty details today, but basically there is a general rule of chemical bonding that elements like to have, for reasons we will get into later, elements like to have 8 valence electrons. Okay? It's not a conscious decision. They don't have brains, right? They're not really thinking about it. It's due to the electrostatic interactions. Like I said, we're going to get into it when we look at things in more detail. But basically, elements like to have 8 valence electrons. Okay? So, what happens here is chlorine steals the electron away from sodium. All right? So I'm going to represent that by circling the electron and drawing an arrow, moving it over to chlorine there. Okay, so by doing that, chlorine gets 8 valence electrons, which, like I said, is something desirable for most elements. Okay, and what you may not realize yet, sodium also is getting 8 valence electrons. Okay, and let me show you how. All right, let me go back to this slide here. Here's my Bohr model of sodium, right? Here's my 1 valence electron. If the 1 valence electron from sodium leaves and goes to chlorine, what's left is an empty energy level, okay? And an empty energy level is empty, okay? It's no longer the valence level for that atom. So underneath, there are 8 more electrons, which become the new valence electrons, okay? So that is one way that this works, okay? Sodium with 1 valence electron gives its electron over to chlorine, and in doing so, both atoms achieve that 8 valence electron situation, okay? Which, like I said, for reasons that we're going to get into later, that is a desirable thing, all right? So, let's go back to the document camera here. All right, so the after stage could be drawn in a couple of different ways, but the way that I tend to draw it is like this, okay? Now, I don't draw the 8 new dots on sodium, okay? When I empty this one out, I kind of just leave it empty. But I will go ahead and draw the 8 electrons around chlorine, okay? So like my total number of valence electrons is sort of staying the same, okay? I know that sodium does have the 8 valence electrons underneath. It's just sort of implicit. I'm not going to actually draw the new ones there. Okay, one other thing that we need to consider, okay? What has happened here is the number of electrons on each atom has changed, okay? Sodium went from having 11 protons, which are positive, and 11 electrons, which are negative, to having 11 protons and 10 electrons, okay? Because it lost an electron, right? Let's do the same thing for chlorine. Chlorine went from having 17 protons and 17 electrons to having 17 protons and 18 electrons. Okay? The protons don't change. Okay? If an element is sodium, then it has 11 protons. Okay? That's its atomic number, period. And it started here with 11 electrons. But when it loses that electron, okay, when it loses that electron, it's now down to 10. Okay? And chlorine, which started with 17, is now up to 18. Okay? Now let's look at the consequence of this. If I look at these two situations here, we've got an issue, okay? Sodium now has one more positive charge than negative charge, meaning that this atom now has a positive charge of 1, okay? And it's the opposite case for chlorine. Chlorine has one more electron, one more negative charge than positive charge. So the chlorine atom now has a negative charge of 1, okay? These are called ions, okay? Ions are charged atoms, okay? They're atoms that have a positive or negative charge, okay? These over here would be neutral atoms. These are ions, okay, that have an overall positive or negative charge. What happens when you have oppositely charged objects, right? Say a positively charged sodium ion and a negatively charged chlorine ion. Well, they're attracted to one another, right? Oppositely charged things are attracted to one another. We saw that when we learned about Coulomb's law. So these two guys here stick together, okay? And this is sodium chloride, okay? It is different than the pure sodium and the pure chlorine. The exchange or the transfer of the electrons has not only caused these to stick together, but it has also changed how they behave. Okay, because like I said, sodium chloride, salt, is very different than pure sodium and pure chlorine on their own. So that is an example of ionic bonding. Okay. So once again, an ion is an atom with an overall positive or negative charge due to its loss or gain of electrons, and an ionic bond is the electrostatic attraction between atoms which arises due to the transfer of electrons, right? So when the electron moved from sodium to chlorine, we created these oppositely charged ions, one positive, one negative, and it's the electrostatic attraction between those ions that is the ionic bond, okay? There's no sort of special thing that's being created here. It's just the attraction that those two ions feel together towards each other. They're now acting as a single unit, right? They're sort of stuck together. That is what the ionic bond is, okay? And really quickly, because I know my video is lengthening here, really quickly, I want to get into the next example here, okay? So this is, let's look at the product of a chemical reaction between magnesium and oxygen. Typically in class, I would do this reaction in front of you because it's pretty cool. So you can actually take magnesium and oxygen gas. So you would have a little strip of magnesium metal, oxygen gas in the air, and you light it on fire. Okay, that little triangle there means add heat. And you will form a new chemical called magnesium oxide. Okay? And technically, in order to balance this equation, I need to add some coefficients there. We'll learn about that later. But this right here is the chemical we're going to look at. This is magnesium oxide, which is composed of magnesium and oxygen. Okay? So, what's going on here? Well, once again, the first thing I really want to do is draw my dot structures. Okay? So take my word for it. Magnesium has 2 valence electrons. Oxygen has 6. Once again, it's not a huge deal how you draw these. Okay. And so once again, we're going to learn more about this later, but the ideal situation for both of these guys is to have 8 valence electrons. Oxygen, in this chemical reaction, takes 2 of the electrons from magnesium. Okay? In doing so, oxygen ends up with 8 valence electrons. That's clear to see, right? 6 plus the 2 from magnesium. And then just like sodium, right? Remember when the 2 valence electrons from magnesium leave, there's the shell of electrons underneath, okay? And so even though magnesium appears to have no valence electrons here, that's actually not true. It has 8 valence electrons that are underneath that shell there, okay? Now, what would the charges be on these atoms? It's going to be different than this scenario here. With this scenario, we only transferred 1 electron, so our charges were +1, -1. In this scenario, magnesium has lost 2 electrons. Okay, we've subtracted 2 negative charges from magnesium. So kind of like in math class, if you subtract a negative, you're actually adding. That's kind of the same principle here. If you're subtracting 2 negative charges, then you actually end up with a positive 2 charge. And if you're gaining 2 negatives, like adding a negative number, then you're actually subtracting, right? So we end up with a stronger attraction here because these charges are bigger, right? And if you remember Coulomb's law, the bigger the charge, the stronger the attraction. So there you go. That's a new chemical here. Magnesium is a metal. Oxygen is a gas. Magnesium oxide is kind of like chalky. It's kind of like a white chalky substance. It really does feel like chalk. Okay, and when we end up back in the classroom, hopefully next semester, I will do this reaction for you guys, and you can play around with it a little bit. Okay? All right. So, I'm almost done. I want to get into the next little thing just a little bit. I do apologize. I was trying to make this shorter. The good news is you're not going to have a ton of work to do for me related to this, at least not on Thursday or Friday. Okay, let's look at one other type of bonding. Okay, so that was ionic bonding. There is another type of chemical bond called a covalent bond. Okay? So, just to back things up a little bit. Ionic bonding occurs when there is a transfer of electrons, when electrons move from one atom to another, like a distinct, clear transfer. Covalent bonding is different. Okay, covalent bonding arises when the sharing of electrons occurs. Okay, when the sharing of electrons occurs. This is a bit more complicated to understand, but basically we're still going to be trying to reach that that 8 valence electron situation. Okay, we're going to get into more details of it later. But okay, so basically we're going to be sharing electrons instead of there being a transfer. I think this works a lot better when we just get into an example. Okay, so let's look at this example here, methane. Okay, so let me get a new piece of paper here. This is truly one of my favorites. I do love methane a lot. Okay, so the chemical is called methane. And as you saw on the slide there, the chemical formula is CH4. Okay? Typically, the way that these are drawn is whichever atom comes first, especially if it's carbon, that's going to be in the middle. And whichever element comes next, usually if there's like a number with it, then that's going to go around the outside. Okay? Okay, and we're going to draw our dots on there, our valence electrons. Hydrogen has 1 electron, period, which happens to be a valence electron. And carbon has 4 valence electrons. Okay? Okay, and like I said, we're trying to, instead of transfer electrons this time, that's not what happens in methane. In methane, what we see is a sharing of electrons. Okay? And we're still trying to achieve that 8 valence electron situation. And so here's how it works. The 1 valence electron from hydrogen will team up in a pair with the 1 valence electron from carbon, and they will be shared in between the hydrogen and the carbon. And this happens 4 times. Okay? And I'm drawing some nice little boxes here. We're not always going to draw it like this, but just for the first example here, that's how I'm going to draw it. So they get shared together in between. So these pairs of electrons get shared in between the people that they originally came from. Okay? In doing so, carbon gets to feel as if it has 8 electrons, right? It started with 4 of its own, and it's adding on this 1 electron from hydrogen. It's not completely stealing it, like in the ionic bonding situation. Hydrogen is just being generous and is allowing this electron to sort of exist between the two, and carbon is also donating to hydrogen. Okay, so if I count things up here, carbon has 1, 2, 3, 4, 5, 6, 7, 8 electrons that it feels like it has. Each hydrogen only has 2, right? This hydrogen here has these 2 electrons. This hydrogen here has these 2 electrons. Sometimes this is actually drawn like this, okay, where the electrons are, instead of drawn in like a line like that, sometimes it's drawn like that. Other times, depending on where you're looking, it's drawn like this, where the pairs of electrons are replaced with lines, okay, where this boxed thing of electrons is replaced with the line, okay, but it means the same thing, okay? So all you really need to know here is that those lines or these electrons are being shared They are shared electrons between the two partners there. Okay? So why does hydrogen only get 2 electrons? Well, if I go back to my slides here, and I go way back to my Bohr models, the first energy level can only hold 2 electrons, right? Because there's only the 1s orbital. Okay, so hydrogen and helium, they're the 2 elements that sort of break that rule of wanting to have 8 valence electrons. The other elements, especially these bigger elements here, like all of these nonmetals, they want to have 8 valence electrons as a general rule. Okay, but hydrogen and helium do not. There's just no room for there to be 8 valence electrons here. Okay, so that's methane. I'm going to quickly show you a few other examples. Let's look at water. This one's kind of cool. Okay, water, another favorite chemical of mine. Water, H2O. We've got oxygen and 2 H's. I know I said before that this first one typically goes in the middle. Perhaps a better rule would be hydrogen is always going to be surrounding the other atoms. Okay, so if you have hydrogen in a chemical, it is almost always going to be on the outside, and something else like carbon and nitrogen, oxygen, those are going to be sort of the central atoms that have the hydrogens branching off of it, right? Because hydrogen, as we saw up here, each hydrogen can only make 1 bond. Okay, so let's take a look at H2O. Oxygen has 6 valence electrons. Each hydrogen has 1. And it's going to be the same thing, right? Oxygen is going to try to get to its 8 valence electron situation by sharing an electron with hydrogen, who also shares an electron. Okay, and so if I draw this in sort of my other ways of drawing it here, you can see that the oxygen in the middle ends up with 8 electrons, or 8 valence electrons, and each hydrogen ends up with 2, right, which is the ideal situation. Okay, and then I think I have one final example that I'd like to show you, maybe 2 more. These are going to go quick. We're going to do both of these together. So we're going to look at carbon dioxide, and then we're going to look at molecular nitrogen. Okay, so we're going to do both of those sort of back to back. Okay, so carbon dioxide, CO2, and then molecular nitrogen, N2. All right, so here we don't have any hydrogens. Carbon is always going to be in the middle. Okay, so if you do have carbon, that is always going to be in the middle. Lots of little nitpicky rules in chemistry. So I'm going to put my 2 oxygens on the side here. Let's put my 4 valence electrons on carbon, my 6 valence electrons on oxygen. And let's see how we can try to connect these together, how we can share these electrons together so that each partner gets 8 valence electrons. Well, carbon only has 4, so carbon is going to need to share all 4 times in order to get to 8 valence electrons. Okay, if it shares 2 times with each oxygen, that's also going to bump oxygen up from 6 to 8 as well. Okay, so here is the final picture. Okay, and if you draw this on your own piece of paper and it looks a bit different, that's okay. Like I said, this is really supposed to just be sort of an introductory day. If I draw this in my other sort of models or my other styles, I might have something like this. So I have 2 pairs of shared electrons. This is called a double bond. Okay, so that would be represented like this. Okay, or if I draw it with the lines, this bottom way tends to be the way that I prefer to draw things. Like this. Okay, notice how I still have these unshared electrons on here. That is important. Okay, so these electrons here, I'm still drawing those. They are still there. Okay, so this is an example of a double bond. Okay, and actually we have 2 double bonds there. Okay, and that's carbon dioxide. Okay, let's look at N2. This is nice and simple. N2. This is actually about 80% of the atmosphere. Okay, so you're breathing this in constantly. And you're breathing it right back out because it does not interact with anything in your body. Okay, it's like an inert gas. It does not mess with you whatsoever. Nitrogen starts with 5 valence electrons, and so if they each have 5, The only way to get to 8 would be to share once, share twice, share 3 times. Okay, and this would be an example of a triple bond. Okay, so if I were to draw this in my other styles, I would have a triple bond there, or in the way that I prefer, in the way that we will generally do things, a triple line like this. Okay? So, let's sort of wrap things up here. I'm just about done. I know I've breached 30 minutes here, and I really did not mean to do that. So let's go back to the covalent bonding slide here for just a second, and we'll wrap things up. So covalent bonding is the chemical stability that arises due to the sharing of electrons. That 8 valence electron situation is energetically desirable. Okay, we're going to learn more about that later. And so achieving that configuration is how covalent bonds form. Okay, so a covalent bond is technically like shared electrons between 2 atoms. A molecule is a group of atoms that are covalently bonded together. Okay, so like water, you can have water molecules, which consists of 2 hydrogens bonded to a single oxygen. The structural formula, okay, as opposed to the chemical formula, right? So a chemical formula would be something like this. A structural formula are the things that we just drew. Okay, those are formulas which illustrate the arrangement of atoms in a molecule of a compound. Okay, the arrangement along with the types of bonds that exist between them. Okay, all right. So 32 minutes, not the worst. Pretty bad though. Like I said, the good news is that we're not going to have a ton of work to do with this specific lesson. We're just going to mainly do a few little activities together in class. We'll get into some of the nitty-gritty details of ionic and covalent bonding in our upcoming videos. Okay? Thanks for watching, and I will see you next time.